And these are the few examples. This is the half order derivative of t to the power half, and this is the half order derivative of t. And it is very remarkable that the fractional derivative of a constant is not zero. Instead of that, it is a function of t. And this is the first integral that we everybody know, that is integral 0 to t fu du, the second integral, and n times successive integral. This n times successive integral can be written in the closed form by Cauchy form with the help of factorial gamma function. So this is 1 by gamma n integral 0 to t minus u t minus u to the power n minus 1 fu du. So uh, So in this concept, with the help of this concept, the Riemann-Leibel fractional derivative is of order alpha, where alpha lies between 0 to 1, is given by this is the operator Riemann-Leibel fractional integral operator J alpha of order alpha over the function ft. This is 1 by gamma alpha integral 0 to t minus u alpha minus 1 fu du, where t greater than 0. Now, fractional derivative of order alpha can be defined in two ways. Many ways it can be defined. These two ways are mainly important. One is Riemann-Leibel fractional derivative. If you take the fractional integral of order 1 minus alpha over the function ft, and then if you take the first order derivative, then it will be Riemann-Leibel fractional derivative. And if you take the first order derivative over the function ft, and then you take the fractional integral of order 1 minus alpha, then we get to the Caputo fractional derivative. Now you can see that the fractional derivative, unlike the local derivative, it is not a it involves actually integral. So it is not a local operator. It is a non-local operator. So since it is a non-local operator, so time fractional derivative of a function ft at the time t equal to t1 requires all the past history. That is, it requires all the values of ft starting from t equal to 0 to t equal to 1. And this fractional derivative can be used for modeling the system with memory effect. And space fractional derivative of the function fx, like the time fractional derivative at the point x equal to x1 requires non-local values of fx. So fractional derivative can be used for modeling distributed parameter system also. Now the solution of fractional differential equation can be written in the can be represented in the compact form using the Mittag-Leffler function. So it is actually most of the linear case it can be represented. Non-linear case it is difficult to represent. So what is Mittag-Leffler function? The Mittag-Leffler function, one parameter Mittag-Leffler function denoted by capital E suffix alpha z equal to summation over k from 0 to infinity z to the power k gamma alpha k plus 1, where alpha greater than 0 and mod z less than 1. This is one parameter Mittag-Leffler function, and two parameter Mittag function is E suffix alpha comma beta z summation over k from 0 to infinity z to the power k by gamma alpha k plus beta. Now, this time fractional diffusion wave equation has been solved by analytical method, and it can be represented by Mittag-Leffler function. So let us discuss the typical. Let us consider the typical time fractional diffusion wave equation with initial condition u x0 equal to sin x for x greater than 0 less than pi, ut x0 equal to 0 for x greater than 0 less than pi, where alpha lies between 1 to 2 with Dirichlet's boundary condition. Hence, the boundary condition is homogeneous. U0 t equal to u pi t equal to 0 for t greater than equal to 0. This equation has been solved by me by atomic decomposition method, and this paper has been published in the year 2010 in the Physical Scripta, and I have obtained this analytical solution. Uxt is summation over r from 0 to infinity minus t to the power alpha r by plus 1 sin x. And this solution can be represented in the compact form using the Mittag-Leffler function like E alpha minus t to the power alpha sin x. So this can you see the animation? Hello.
Yes, yes,
Okay.
sir, we can see.
So this animation figure represent the behavior, fractional order behavior of the nature of the solution. When you can see when the alpha is near lies between 0 to 1, then its behavior shows diffusion behavior. And when it lies between one more than one and less than two, 1 to 2, when alpha lies between 1 to 2, it shows the wavy nature. Next is in the year 1986, the Riemann-Neville fractional derivative has been approximated by the researcher Lubitsch, whose paper has been published in the CRM Journal of Mathematical Analysis, and he shows the fractional derivative, Riemann-Neville fractional derivative can be approximated with higher order of order P. Now, in the year 2011, the notable researcher Lee, Chen, and Lei approximate the Caputo derivative with higher order approximation. In my talk, I will discuss the higher order algorithm for Ries fractional diffusion equation and space Ries fractional Fokker-Planck equation. Now, first I introduce the Ries fractional derivative. What is Ries fractional derivative? In the year 1993, Shamko et al. Introduced Ries fractional derivative of the function fx of order alpha. The Ries fractional derivative can be expressed as a linear combination of the left Riemann-Neville derivative. This one is left Riemann-Neville derivative, and this is right Riemann-Neville derivative. And what is the advantage of this? This considered the two-sided derivative. One is Riemann-Neville derivative, left Riemann-Neville, and right Riemann-Neville derivative. And here, because here the domain is minus infinity to plus infinity. And here the initial condition is not required. This is also an advantage for Ries fractional derivative. And this fractional derivative has a important, this is required for to represent or to approximate the fractional Laplacian, which is a mathematical operator which required for modeling of physical phenomena like anomalous diffusion and to modeling the space quantum mechanics, space fractional quantum mechanics, or in the formulation of fractional Schrodinger equation, which is required to describe the quantum system. So this is the Ries fractional derivative in the domain A to B. This is finite domain. This is finite domain, and this here also it is a linear combination of left Riemann-Neville derivative and right Riemann-Neville derivative. Now the lemma 1, this lemma shows the when the function lies between the space, belongs to the space, continuous space whose fifth order derivatives are continuous, and all the derivatives up to fifth order belong to the Lebesgue space L1R, then the function fx can be discretized using fractional centered derivative. So this is the notation of fractional centered derivative delta alpha fx is equal to summation over j from minus infinity to plus infinity gj fx minus j h, where gj coefficient is minus 1 to the power j gamma alpha by 2 minus j plus 1 gamma alpha by 2 plus j plus 1. So using this fractional center difference approximation, we can approximate the Ries fractional derivative. This is the Ries fractional derivative of order alpha of the function fx when h tends to 0 and alpha lies between 1 to 2. In the year 2012, notable researcher Chelik and Dumen shows that if the function is defined in the finite domain AB, then also the Ries fractional derivative can be approximated using the fractional center difference approximation given by this equation. And the order of this approximation is second order. And here, in the year 2006, famous researcher Michiat and Tejeron proposed the shifted world formula which approximate the Ries fractional derivative, and but the order is first order approximation. This is first order approximation. Now, let us consider the inhomogeneous rich fractional diffusion equation given by equation 1 with the initial condition Wx0 equal to phi x, where x greater than equal to 0, less than equal to capital N, and with the boundary condition, homogeneous boundary condition W0t equal to WLT equal to 0, where t lies between 0 to capital T. Here, alpha is the rich fractional derivative, alpha is the order of the rich fractional derivative, here, and alpha lies between 1 to 2. So this type of super diffusion problem largely arise in modeling of fluid flow, finance, and other applications. So to solve this type of least fractional derivative, least fractional diffusion equation, first we discretize the domain, spatial domain 0 to L into M subintervals by the step size H equal to L by M, and the mesh point XL equal to LH for L equal to 0 to M. And WLK is the computed value of WXL at the mesh point XL And here I have used the explicit finite difference approximation to discretize the Riesz fractional diffusion equation, equation 1. And discretizing the equation 1, I have obtained equation 2 using the, here I have applied shifted Gruel formula. So equation 2 can be represented in the matrix form given by equation 3. Here A is the matrix, symmetric matrix M-1, M-1 symmetric matrix. And again, I am telling this scheme is given by equation 3. It is a explicit finite difference formula. Next is time space fractional focal point equation given by equation 4 with initial condition x0 wx0 equal to phi x, where x greater than equal to a, less than equal to b, and with the Dirichlet's boundary condition. Here also it is a homogeneous boundary condition wat equal to wbt equal to 0 for t greater than equal to 0, less than equal to capital T. And here k alpha mu is the Almondras diffusion coefficient, m is the mass of diffusing test particle, and d prime x m eta alpha is the drift coefficient. When the capital Vx, that is the potential function, is constant, then it will become a Riesz fractional diffusion equation 1, and alpha equal to 1. And when alpha equal to 1 and mu equal to 2, it becomes the standard Fokker-Planck equation. Now, to solve the equation 4, again we shall discretize the spatial domain, and here we shall consider non-linear drift coefficient, and we shall approximate the Riesz fractional derivative by fractional central difference approximation. So order of the approximation is second order, and we shall I have discretized the time derivative also central difference approximation given by equation 5. So using equation 5 and the lemma 1, I have obtained the equation 6. This is the implicit finite difference equation. And here the truncation error is order of tau square plus a square. And this equation, I think equation 7 is, this is equation 7. So this equation, this is not 7. Anyhow, this equation is actually implicit finite difference equation. Here, each alpha is the each AI is the symmetric matrix of order m-1 by m-1. And to discuss the convergence analysis of this finite difference approximation, finite difference method, here I define the space function space, one function space that is capital lambda gamma, where gamma is the domain of the fractional differential equations, that is a comma b cross 0 comma t. So this is the typical example for Riesz fractional diffusion equation. Here initial condition is wx0 equal to x square into 1 minus x whole square, where x greater than equal to 0, less than equal to 1. And the Dirichlet's boundary condition is w0t equal to w1t equal to 0 for t greater than equal to 0 and less than equal to capital T. And the exact solution is this: wt equal to 1 plus t to the power alpha x square into 1 minus x to the power square. And this problem has been solved for the parameter capital K equal to 1, tau uh, time steps tau has been taken, temporal steps tau has been taken as 0.001, and spatial step h has been taken as 0.05, and fractional order alpha has been taken as 1.5. So figure 1 shows the comparison of with the exact solution for time t. You can see that there is a very good near agreement between the two solutions. Here, the figure 3 represents the comparison of numerical solution, exact solution for alpha equal to 1.5 and for t equal to t. Is the slide is visible to all?
Yes, sir. Yes, we can
Hello?
see. Yes, we
Okay.
can see.
And figure 3 represent, sorry, figure 3 represent the comparison of numerical solution with the exact solution. Sorry, comparison of numerical solution obtained by explicit finite difference scheme with the exact solution for time t equal to 5. And this animation figure shows the physical behavior of the solution for different fractional order alpha. So we can see that when alpha is increases, then diffusion behavior increases. With the increase of alpha, diffusion behavior increases. Next example is a time fractional Fokker-Plan equation, rich space fractional differential equation given by equation 8, where initial condition Wx0 equal to k alpha to the power k alpha mu x square 1 minus x square, x greater than equal to 0, less than equal to 1. And also I have taken the Dirichlet's boundary condition, and this has been solved using the implicit finite difference scheme. And the figure 4 shows the comparison of numerical solution obtained by implicit finite difference scheme with the exact solution at time t equal to 1. Here the parameter has been taken as k alpha mu equal to 25, and temporal step tau has been taken as 0.0001, and spatial step h has been taken as 0.0.5, and alpha has been taken as 0.8 and mu has been taken as 1.9. So there, figure 5 also represent the comparison of numerical solution obtained by implicit finite difference scheme with the exact solution for time t equal to 3. So from these two figures, we can see that there is an excellent agreement between the exact solution and the numerical solution. Figure 6 represents the comparison of numerical solution obtained by implicit finite difference scheme with the exact solution for time t equal to 5. Theorem 1 represent the condition of stability, stability condition for explicit finite difference scheme. 3 for solving the rich fractional diffusion equation. So here the stability condition is mesh factorization R, that is tau by alpha h to the power alpha, that should be less than equal to 2 by 2 by k into g1 minus g2 by cos alpha pi by 2. So this theory has been proved in my paper, which is published in the year 2000 Journal of Computational Nonlinear Dynamics, ASME journal. It has been shown that implicit finite 6 for solving the space fractional Fokker-Plan equation that is unconditionally stable. And theorem 3 using the implicit finite numerical solution, numerically computed solution converges to exact solution, and the order of the solution, and it converges unconditional. Now we skip the third order numerical scheme. Let us move on to the fourth order numerical scheme. Till now I have discussed the first order numerical scheme for rich diffusion equation, second order numerical scheme for rich space fractional Fokker-Plan equation. Now I am going to discuss the fourth order numerical approximation. Now the theorem 4 state that if the function u x t lies in the space of continuous function whose the first derivative up to seventh order are continuous, and all the partial derivatives up to seventh order with respect to x belongs to the Lebesgue space L1R, then the Riesz fractional derivative of order alpha can be approximated by this fractional central difference approximation, and order of this approximation is order of h to the power 4. And using the based on this theorem 4, the Riesz space fractional Fokker-Planck equation has been discretized. And after discretizing the equation, I have obtained equation 9. And equation 9 can be represented in the compact matrix form given by equation 10. And this is the implicit finite difference scheme. Here this implicit finite difference scheme is it has been shown in the theorem 4.5 that this scheme is also unconditionally stable, and the order of this approximation is order of tau square plus h to the power 4 because the local truncation error is coming or tau square plus h to the power 4. Let us consider the typical example 3. This is the Riesz fractional differential equation given by this equation, and here the initial condition has been taken as ux 0 equal to 0 and homogeneous boundary condition has been taken. The exact solution is given by t to the power 2 alpha plus 1 into x to the power 4 into 1 minus x to the power 4, and this table 4 this problem has been solved by implicit finite difference scheme and fourth order implicit finite difference scheme. And table 1 shows the order of the convergence order for temporal convergence order and as well as spatial convergence order. Also the L infinity error. This is L infinity error. This is maximum error means L infinity error for different fractional order alpha equal to 1.2, 1.4, 1.6, and 1.8. We can see that for the temporal convergence, it is approximately 2. And for the spatial convergence, it is approximately 4. You can see 3.9, etc. So it is approximately 4. This figure 7 represents comparison of the numerical solution obtained by implicit finite difference scheme with the exact solution for fractional order alpha equal to 1.1. And here the temporal step size is tau equal to 1 by 50 and spatial step size h equal to 1 by 50. So we can see there is an excellent agreement between the two results. Figure 8 also shows the comparison of exact solution with the implicit finite difference scheme, fourth order implicit finite difference scheme, and for alpha fractional order 1.9. So here also we can observe there is an excellent agreement between the two numerical two results. So this figure 3D figure represent the numerical solution obtained by fourth order implicit finite difference scheme for alpha equal to 1.2 for example 3, and same figure can be observed using the exact solution for alpha equal to 1.2. This shows the numerical solution obtained by fourth order implicit finite difference scheme for alpha equal to 1.8. This is the 3D numerical solution surface for alpha equal to 1.8, and similar figure can be observed for fractional order alpha equal to 1.8 for exact solution. So this we required a proper and exact application for the physical behavior of various physical behavior. For explaining the various physical behavior, we require the fractional calculus, which can better explain in compared to other. And it requires the historical dependence or long range interaction. For that, it required the computational time and storage capacity. Therefore, we required an efficient and accurate numerical scheme, and fractional calculus with a stochastic process will better describe the physical behavior. So in future, we have a plan for numerical solution of fractional stochastic differential equation. So first, in the first problem, that is a Riesz fractional differential diffusion equation. shifted rule approximation have been applied, and whose order of approximation is 1. Then fractional center difference approximation has been applied for space fractional focal plane equation, whose order of approximation is second order. Then fourth order approximation has been fourth order implicit finite difference scheme has been applied for his fractional differential equation, and stability and convergence of the numerical scheme has been also analyzed, and the experimental result obtained by different illustrative example shows that there is an excellent agreement between numerical solution and the exact solution. So results are very accurate and and with high precision. So these are the papers in which each fractional differential equation has been solved analytically by optimal homotopy asymptotic method, and that is a semi-analytical method. And in these papers, I have solved these fractional differential equation by numerical methods. And these research work mainly conducted with the funding by the NBHM and ACRB. So I am thankful to both ACRB and PRNS also. These are the references of my presentation. Thank you.
Sir, in the definition of risk fractional derivative,
Yes.
there is cos alpha by 2 in the denominator. Is there
No,
any reason of
cos is there. Cos
I mean,
anything.
dividing by 2 is like averaging kind of thing. But what is the reason for taking cos? I mean, is there any reason or
No. This is the definition, sir.
definition itself? Okay.
This is the definition.
I
Actually,
think so.
this is the definition. Actually,
Yes.
this is actually a definition of reach. If you consider the
Okay.
failure, reach failure, then it will be it can be represented by theta. Theta is called skewness actually. Skewness parameter.
Okay. Okay, sir. Thank you.
Yes, sir. And mod of theta should be less than minimum of alpha and alpha 2 minus alpha. And theta should be not equal to plus minus 1. And this is the reach fractional derivative is the special case of reach failure derivative. Okay, sir.
Okay, sir.
For that, you can consult Richardson book, sir.
Okay, research, sir.
Yes, sir.
Audience, any questions? Okay. Thank you, sir, for your enlightening talk. Your insights are very truthfully valuable, and we appreciate your time to share your expertise with us. Now, I invite Dr. R.K. Sahadev, sir, to facilitate Dr. Sachin Garge, sir, to with certificate. Sorry, I pronounced the name wrong. It's
Anything?
no.
Okay. Thank you.
Thanks. Finally, I would like to invite Ms. Rakhi Dhari to propose the vote of
Thank you, Professor Sahare, for very interesting talk. Sir started with basics of fractional calculus because so many MSc students are also attending. So motivation was there, and then he gave basic definitions of Riemann-Liouville couple kind of thing, and then these fractional derivatives. So many interesting operators are there with applications also. And it is a necessity of solving the differential equations involving such operators. So one always need good numerical methods to solve such partial differential equations.
Yes, sir. Yes, sir.
And even ordinal. So if you see his research articles currently, whatever he shown in the last slides, you can see that these are published in very reputed journals. And as a new researchers, you people can take a motivation from this presentation. And there is always necessity of having good numerical methods for fractional order systems. So please go ahead with these things, and if you have any doubts, you can always contact Professor Sahare sir and proceed. Thank you very much. Thank you, sir.
Thank you, sir. Thank you, sir. Thank you.
Good afternoon, everyone. I am Rakhi Dahalkar, student of second year MSc Department of Mathematics. It is my privilege to present vote of thanks of this today's enlightful talk. First of all, we are deeply grateful to our respected chairperson, Dr. Sachin Bhalekar sir, to gracing presenting our today's session. Thank you, sir. I would like to express my sincere gratitude to our speaker, Dr. Shantanu Sahare sir, for their enlightening talk on higher order numerical method for freeze fractional partial differential equations in anomalous diffusion modeling. Your practical insights and enriching approaches has gratefully enhanced our understanding on this topic. Thank you, sir. We are truly appreciate your valuable contributions. Now, a heartfelt thanks to Dr. Smita Acharya ma'am, a chairperson of this national seminar, and Dr. Prashant Gade sir, coordinator of this national seminar, Dr. Ganesh Kedar sir, convener of this national event, national seminar, and all the respected guests for their valuable time and support. I am also thankful to all respected teachers and organizing team coordinators of this event for their planning and peaceful execution of this event. Finally, finally extended my sincere appreciation to all research scholars, dear students, for their enthusiasm to make this event meaningfully. And once again, thanks to all. We look forward to more such inspiring and knowledge enriching sessions in the future. Have a great day to all. Thank you.
Now, we will have 5 minutes debate, and last debate of your program is validating function. Start at PM. Please come back soon. Thank you.
5 मिनट का टी ब्रेक है तो त्याने झाले बाहेर
ब्लॅक वाली सर बाहेर शेअर आहे नाही
टीम मध्ये boys कुठे गेले?
ऑडिटोरियम मध्ये कुठे गेले रे मस्त अरे सांगतो हमारी गर्ल
Employment.
थोड़ा से कम चल हमारे थ्योरी है थोड़ा से
नाही.
भी नहीं ये नहीं सुनो ये तिथे
हे होते.
दादा तुम्ही तिवारी केअर घेऊन घ्या मी तर म्हटलं जाय
कांदो में वायरस साथ चे
बाहेर पावर एक
बाहर है सर एक चे इधर होंगी हो इकडे इकडे इकडेच आहे ना आणू एक अंदर
हो. नाही एवढे
हा हा तिकडे झाला ना खाली जास्त का ठीक आहे ते विजेता
गाडीचा नंबर लक्षात राहा. गरम झाली. मला ते वेगळ्या कारणास्तव नाही आलं. मला ते वेगळ्या कारणास्तव नाही आलं. हो, तेच पाहिलं. हे- गाडी मोटरसायकल मोटरसायकल पण नाही चालवलीच तर याची नाही. रिक्षा नाही, ट्रॅक्टर नाही. संभाजी बबन भोसंकांचा नंबर घेतलाय का? ऑनलाईन नायट्रोजन केलेले त्याच्यामध्ये एवढा ते मस्त पाच तासातच पोहोचले नाशिकला टाइम हा गेला स्पीडने गेला काय कॅमेरा होता छोटे कॅमेरे फक्त जेवढ्या याच्यामध्ये पाहिजे त्यांनी खरं हे जे कॅमेरे डायरेक्ट सॅटेलाइट नाही हे सॅटेलाइट हे वायफायचे आपण जिथं जेवायला थांबलो होतो तिथून तिथे 200 किलोमीटर राहिलं. हा? गाडी बाजूला नाही तर गाडी बाजूला घ्या मला उतरू द्या. मग डायरेक्ट बजरी सुरीचा परवडेल का? गाडी 100च्या पुढे काही पण नाही ना कशासाठी गाडीचा बी खराब होतो आपला जीवात लोक देतो. अजून ट्राय केला मला पुढे दाखवतो ना तुम्हाला. काहीतरी पण पुढे बसून पाहतो. हा? नाही, नाही. हा? कोणता? Practical. त्याला काय असेल वरती जायचं. कोणती जाते? मग काय ना आपण चढलो ते. हा क्लास आहे. हा? हा? पुढं समृद्धीला चढल्या चढल्या भैयाचा फोन आला होता. हवा चेक केली का असं? तो 4:25चा फोन. आणि पानं घ्यायचा फोन होता तो 3:51चा फोन. जे ज्या वेळेस तुम्ही माझ्या घरी आले होते असं समजा तुम्ही. 3:35 का 3:36 माझ्याकडे आले. आता आपण 100 किलोमीटर चालला. तोच एक्झिट आला ना त्याला तुम्ही उतरले का नाही? अमरावतीचा नाही येणार अजून. हा यवतमाळचा असेल. हा, ते 100 किलोमीटर आलं ना. 82 झालं. हा? बाय बाय. इथं आपण हायवेला लागतो. आता अजून चला सर 21 तारखेला लग्नाला यावं लागेल. इथेच ना अमरावती. हा. रिसेप्शनला बोलवून आणू. रिसेप्शन ठेवायला तिथं काय रोग आला. हा? नाशिकला नाही ठेवणार. हा. चुकून येणार मी. हा? तो आता सनाट पत्रिका वाटत असेल. दररोज कोणाच्या तरी घरी जाऊन पत्रिका वाटून जेवण करून कपडे घेऊन बघा. त्यांना ते आयर गोळा करायची ना आयर द्यायची फार सवय. आज कोणाची पत्रिका पाहिली ना मी. त्याच्यावर असं होतं कपड्यांचे भांड्याचे आहेत स्वीकारले नाही जाणार नाही तसं नव्हतं लिहिलं. हा? नाही वाढवणार नाही ते ऍक्वायर करताना तेवढी एक्स्ट्रा मध्ये ऍक्वायर करतो. त्यांनाच तिचं टेटलीवर एखादं काही स्टॉल बिल टाकायचं कोणत्या दुकान टाकायचं ठरवलं.